Hi guys, it's Vasya here again, and today we will be solving the second problem from the IEEEXtreme contest, which is the Quipu or Quipu function. I don't know how to read it. Anyway, I think it's Quipu, but it looks like Quipu, whatever. So, for the purposes of this problem, I will be making two videos. One will be me describing the problem and the solution with words, and then in the next video we will be coding it, and I will be also explaining the code. One of the reasons is that this problem is a bit more complex than the previous one, and also I don't want to make the same mistake like last time and have a video of 35 minutes long. So let's get into it. The Quipu function is a function which, for a given number n and a given number d, asks us how many divisors does n have which are not divisible by d. Okay, so that's the function, and the problem actually asks us to find the Quipu function for all I between a and b. D is for a particular test case, d will be fixed. Okay, so we cannot do brute force here, brute force approach, and simply iterate over all numbers, and for every number try that number's divisors from 1 to that number, or even from 1 to that number's square root, which is possible, because we will end up with a solution of complexity of at least 10 to the power of 11, right? Because we have 10 to the power of 5 is the range, so we iterate over all numbers between a and b. And then even if we go up to the square root of each number, in the worst case we end up with a complexity of 10 to the power of 5 times 10 to the power of 6, which is not good. So the correct approach here is to use prime factorization and prime number sieves to solve this problem. So that is a prerequisite. You need to know something, not too much, but a bit about prime numbers and prime number sieves. Okay, let's see an example and see why we need the prime number factorization. Actually, what we need is the number of divisors, right? So let's see how the number of divisors is related to the prime factorization. Let's take an example. Okay, so I have a number here which will be 4,235,000, and this number's factorization is equal to 2 to the power of 3 times 5 to the power of 4 times 7 to the power of 1 times 11 to the power of 2. Okay, now there is a formula which gives you the number of divisors of a number from its prime factorization, and let's call this capital X. So div count will be our imaginary function that finds the number of divisors of x is equal to, now what do? We take each of these exponents here we have 1 and here we have 2, add 1 to them and multiply them. Okay, so 3 plus 1 times 4 plus 1 times 1 plus 1 times 2 plus 1, and this is equal to 120. This means that this number has exactly 120 divisors. Now, that is all correct, but the Quipu function asks us to find the number of divisors which are not divisible by some prime number d. So Quipu of this number x and some d, let's say that d is, for example, 5, okay, is equal to, so now how do we get all divisors that do not include this prime number here? Well, all we need to do is remove from our formula the exponents which are referring to that that prime number, right? So here we have 5, so we need to remove this from the formula, right? So if we exclude this, all that remains will be all divisors which do not include d. So how do we do that? We can either simply delete it like this, or we can divide this result by this, and we get the same answer. So it will be div count, so Quipu function of of x and d will be actually div count of x divided by the number of times d occurs in the prime factorization of x plus 1. So 5 occurs 4 times plus 1, which is equal to, all of this is equal to 24. So the Quipu function of this number and d and 5 is 24. Now we need to do this for the entire range. Well, the entire range is not that big. Remember from the problem, the entire range is only 10 to the power of 5. So we can iterate over all numbers once we have the prime factorizations of every number in the range. And for each number, we can calculate this formula. And we can also see how many times d is a multiple of that particular number and divide this by that number. Okay, what we did here. So that's done. That is the problem. Now, what remains is how do you find prime factorization of all numbers in the range? Remember, the range can be really, really big. Well, we can use something that is called segmented sieve of Eratosthenes. Yeah, I think it's called Eratosthenes. So, if you do not know regular sieve of Eratosthenes, then I'll post a link in the description where you can look it up. It's not difficult at all. Basically, what a sieve does, a basic sieve, is given some number n, it will find all prime numbers between 1 and n. How it does that is it filters out all the non-prime factors, and all that remains are the prime factors, the prime numbers, sorry, not factors. All that remains is the prime numbers. Now, that works from 1 to n, but if we want to do here the same, we cannot, because b can be 10 to the power of 12, and if we want to iterate all numbers and find the primes from 1 to b, it will time out. There's no way. Okay, and the sieve itself, the regular sieve, has complexity of n log n, so there's no way that it will pass. Like, it will be 10 to the power of, I don't know, 14 or something like that. No idea. Anyway, yeah, so let's see how this will work. Let's take an example. For example, if a, from the problem a, right, we have a range a and b, a is equal to 40 and b is equal to, b is equal to 50. What else? Let's say that, well, we don't care about d yet. We don't care. We only want to find the prime factorization of these numbers. So what we need to do is find all the prime numbers up to square root of b. Okay, so square root of b is equal to 7, round it down. Okay, that means that we need to find all the prime numbers. Now here we will use a regular sieve to find all prime numbers. So let's see, primes is equal to 2, 3, 5, and 7. Okay, these are all the prime numbers up to 7. We will use these primes to sieve through the range. We will see how in a moment. Okay, let me open up an example that I have prepared here. This is just for reviewing purposes. Don't look at that. I will be explaining with these numbers here. So here's the range. A is 40 and B is 50. Okay, here are the primes and here's the range. Now, what we do is start with the first prime. The first prime is 2. Find the first number in this range that is divisible by 2. This is 40. Okay, so 40 is divisible by 2, yes. Here we will add the prime factorization. Okay, so yes, 40 is divisible by 2, we get 20. 20 is divisible by 2, we add another 2, we get 10. 10 is divisible by 2, we get another 2, we get 5. 5 is not divisible by 2, we continue. Now, we do not iterate over all numbers, but we make jumps of this size, of 2, of 3, of 5, of 7. You will see. Now 42 is divisible by 2, yes, we get 21. 21 is not divisible. 44, yes, we get 22. 22, yes, we get 11. So we add one more 2 here. 46, yes, we get 23. 23, no. 48, yes, we get 24. Okay, 24. 24, yes, we get 12. 12, yes, we get 6. 6 is still divisible by 2. We get 3. Sorry. And 3 is not divisible by 2. We go on. 50, yes, we get 25. 25 is not divisible. Okay, so here I'm writing the prime factorization, and here I'm writing what remains of these numbers. Now we are done with the 2, we go with 3. Okay, so 3, find the first number in this range that is divisible by 3. Which number is that? That should be 42. Yeah, so this is the first number that is divisible by 3. Actually, it is already 21. So 21 is divisible by 3. So we write here 3. And what remains is 7. 7 is not divisible. Now, we keep making jumps of 3. So 1, 2, 3. 45. 45 is divisible by 3. And we get 15. 15 is still divisible by 3. And we get 5. So we write one more 3 here. Again, we jump 1, 2, 3. 3 is divisible by 3. So we get 1. We are done with this number. And that's it. We don't have any more numbers in this range that are divisible by 3. We start with 5. Which is the first number that is divisible by 5 from this range? It is 40. Okay. So we write 5. Actually, it was 5. It was 5. So 5 is divisible. We get 1. 5. The next number, 40, 45. Okay, which is now 5. Yes, correct. We write 5 here. 45. We go to 50. 50 is already 25. It is divisible, and it is divisible again by 5. So we write 2 5s here, right? 50 is 2 times 5 times 5. Okay. 7. Which number here is divisible by 7? So 42 is the first number that is divisible by 7. Yes, it became 7 already, so we'll write here 1 7, and it becomes 1. 42 plus 7 is 49. 49 is divisible by 7. So we write 7. We get what? 7. 7 is divisible by 7. We write 1. And here we write another 7. Yes, that is correct. 49 is 7 times 7. Or 7 to the power of 2. Now we are done. We don't have any more numbers here to sieve. But notice this. We never touched 41, 43, and 47. This means that those numbers are prime. So we can simply write them in their own prime factorization. So 41 is 41. 43 is 43. 47 is 47. And yep, all of the others became 1. Oh, sorry, we missed something here. Aha, yeah, okay. So this means that this number did not become 1, okay? Like these numbers, 41 remained 41, so we write here 41. Also, 44 divided by 2 divided by 2 became 11, and 11, we did not touch 11. That means that we need to add 11 here also. So 44 is 2 times 2 times 11. Do we have another example like that? Yeah, we do. Okay, so 46, when we divided by 2, became 23, and we did not touch it. It did not become 1, so we write 23 here. And that's it. I think that's it. Yeah. Okay, so now you see we have all the prime factorizations of each of the numbers in the range. Okay, this is how segmented sieve works. Okay, it means segmented because we are working on a segment of numbers, right, from a range. You can call it range sieve or whatever. And we don't care about the numbers before or the numbers after. We only care about the numbers in this range. For this to work, we need a regular sieve up to square root of b to find all these prime numbers, and then we iterate each prime, and for each prime we iterate this range by starting from the first divisible number by that prime and then making jumps equal to that prime. Okay, so if we were starting with 7, we would make jumps of 7. If we were starting with 13, we would make jumps of 13, because we are jumping from one multiple of 13 to the next multiple of 13. We don't need to care about numbers in between. This algorithm will have a complexity similar to the regular sieve. Basically, we need to iterate over all primes, and for each prime, we need to make these jumps. Okay, so that's it. I think that's all. Yes, this is the idea that we will try to do. After we find this prime factorization, we go back to the algorithm, iterate all numbers from A to B, and calculate this formula, and then find how many times D occurs in the number between A and B that we are checking currently, and divide and add that to the result. That's it. That's all. One thing to notice about this problem is that the memory limit is only 10 megabytes. So we cannot store all the prime numbers and their exponents. It is too much memory. Okay, we need to optimize. What we need to notice that for this formula, we don't really care about the prime numbers. We care only about the exponents. So all we need to keep are these numbers here. Okay, 3, 4, 1, and 2. For example, here, we don't need to store like 2 and 5. We can only store 3 and 1, because we have 3 2s and one 5. Or here, we can store 4 and 1. Here we can store only 2, which means we have some prime to the power of 2. And that's it. That's all. Well, I hope this explanation clears things up a bit. I will post a video after this one where we can code it up, and I will explain the code. Thank you for watching, and see you next time. Bye bye.